Okay, then I think we can start, right? So welcome to the ACM SIGBED SRC Student Research Competition. And today there will be 3 sessions. The first session mainly for North America, because there are different time zones. And then, so the first session will be online. Second session on-site in Shanghai with some physical attendees. And then the third session in the afternoon in Shanghai for the European time zone. So we'll then we can. I think we'll start the first session. So each student, as we have communicated via email, each student will have 10 minutes, 5 minutes precisely for the presentation, and then 5 minutes questions from the judges. And then the judges, please send the score sheet to me immediately after the session, because the results will be announced later tonight in the Yes Week award ceremony, right? So for the sequence, we'll go with the sequence communicated in the email. So then let me welcome the first speaker. Please share your screen and start your presentation.
Sure, yeah, thank you. Let me quickly share my screen and get started. All right. Yeah, hello everyone, I'm Zishen, a third-year PhD from Georgia Tech. And today I'm very glad to present my work on building agile, efficient, and resilient computing for autonomous machines. And as we all know, autonomous machines, including the self-driving cars, UAVs, and robots, are on the rise. And they are gradually becoming part of our lives and deployed in many scenarios. And their revenue is estimated to increase 5 times in the next 5 years. However, this rapid development poses several challenges. These robots need an agile design methodology to adapt the evolving field, and they need to conduct the computation in an efficient way while ensuring their reliability. So to address these challenges, my research takes a cross-stack view and proposes several solutions to improve the agility, efficiency, and reliabilities of robotic computing. And I will use drone as an example and go over how we deal with these challenges one by one. So the first part of my work is agile design methodology for autonomous machines. So for challenges, drone is a complex cyber physical systems, and onboard compute is just one of components. And drones are severely swap constrained. Also, these different components impose a huge design space to us. So the question we're asking and trying to solve here is how to design and select the optimal onboard compute, and how do we automatically navigate this huge design space. So we first propose a performance model for drone system. The model is roofline-like and can help determine which component is the system bottleneck and indicate the optimal design point. We also build an interactive tool based on this model and has been open sourced. And using this model, we propose Autopilot, an intelligent cyber physical co-design automation framework for drones. So it takes the task specs as input and will automatically generate the optimal design configurations. So let's take a closer look, step by step. So the first step is to train autonomy algorithms. So we use drone simulator to train policy and find the good candidates. And the second step is the multi-objective design space exploration. Here we use the Bayesian optimization to intelligently navigate this huge design space and find the algorithm and hardware designs that are optimal in successful rate and compute performance. And the third stage, we will use the performance model to perform the full drone system co-design to maximize the drone mission performance. And let's see some results. So by using the performance model, we can very easily map the different configurations on this roofline and characterize their performance. And we believe that this tool can provide guidance for the whole community to design a better cyber physical system for drones. And the generated design from the Autopilot consistently outperform the other designs under the various scenarios. And it's worthy to note here that this methodology is agile across the different drone steps, environment, and design parameters. And we believe that using machine learning-based methods to automate design flow not only benefits drone design, but also help other cyber-physical systems. So after we have this agile methodology, how do we achieve efficient robotic computing? And this is my second part of my work. So methodology, we first build a unified algorithm framework and do system profiling to determine the acceleration target. And here we use robotic perception and localization as an example. And our framework integrates multiple algorithms such as ORB, SLAM, and VIO. And after profiling, we build a hardware accelerator for efficient perception and localization. And several techniques, including the parallelism, pipelining, and sparsity, are leveraged in this design. And by offloading the perception on FPGA and localization on CPU, we can achieve the high performance, low power, and adaptive characteristics. And here are some example results. So for system profiling, we find that perception has the most latency, while backend has the most variations. We also improved the existing algorithm to become hardware friendly. And compared with the state of art and the CPU and GPU, we achieved nearly 15 times improvement in the best cases. And based on our work, we also published the first survey paper and the first book on FPGA-based robotic computing. And our work serves as one of the main driving forces for the newly built Xilinx Robotic Hardware Acceleration Working Group, and having more and more impact in the whole community. And going forward, we know that reliability is very important for this safety-critical system and applications. So the third part of my work is to enable the resilient computing. So faults can impact the safety in any stages. And here I focus on hardware fault, such as the silent data corruption. So the current fault analysis tool means the error propagation in this end-to-end robotic system. And current fault mitigation techniques usually require the redundancy and will incur the large overhead for these edge applications. So to analyze the fault tolerance of drone system, first we propose the fault injection framework, ROS-FI, that can inject hardware fault and portable to any robot operating systems. And using this tool, we conduct a large-scale fault characterization in both learning-based and model-based autonomy paradigms. And after understanding the fault tolerance, we propose the lightweight application-aware fault mitigation techniques. And the techniques are based on anomaly detection with autoencoder, and also can be portable to any ROS-based systems. So some key takeaways from our reliability analysis. First, we find that the end-to-end analysis is very essential for these cyber-physical systems. So that means we need to let error propagate through the whole system and evaluate its final impact. And we also find that the planning and control stages are more critical. And for the fault mitigation, we demonstrate that our anomaly detection method is able to fully recover the failure cases in the best scenarios. And using our previously proposed performance model, we show that compared with traditional modular redundancy-based method, our application-aware techniques has negligible overhead. And based on our work, recently, I'm very excited to co-found and co-lead the MLPerf Resilience Working Group, where we aim to benchmark the resilience of machine learning and autonomous systems. So to summarize, my research improved the agility, efficiency, and reliability of robotic computing. And our autopilot framework contributes to the CPS design automation. And our Skyline and ROS-FI tool has been open source to help design and resilience evaluation for the community. And our robotic computing book serves as one of the main driving forces for Xilinx ROS acceleration proposal. And recently, I co-found and co-lead the MLPerf Resilience Working Group. And starting my PhD in the 2.5 years after 1 year master research, I have published 1 book, 10 first author papers, 7 co-author papers, and I won the Best Paper Award in the DAC 2020 and the CAL 2020. I'm looking forward to make more contributions in the robotic computing during my PhD. So with that, I will end my presentation. Thank you all for your attention, and I'm happy to take any questions. Thank you.
Thank you, Zishen. A very good presentation. So questions from judges, please. Just unmute yourself and directly ask.
Yeah, very interesting. This is Shun from Villanova. Very excellent presentation on this. Just one question on the on the robotic computing side, right? So what you presented here is mainly based on FPGA. So do you have any comments on what kind of computing platforms would be the best suited for robotic computing? Is it FPGA, ASIC, GPU? What makes it different, right, from the traditional or traditional cyber-physical systems?
Yeah, I think that's an excellent point. So I feel like so for the suitable compute platform for this robotics. So my perspective is really depends on application. Like if you want to design a hardware accelerator with a compute platform for very like tiny drones or the tiny robotics. So in that case, I would say maybe like a cheap basic would be the way to go forward, because the tiny robots is very size, weight, and power constrained and has very resource constraint on board. So in that case, maybe a chip is the a suitable a platform. And for the normal size of drones, I would say for this drone navigation. So because usually the real-time performance is 30 FPS. If you run the very compute-intensive algorithm on the GPU, it can meet this requirement. So in that case, we want the FPGA to accelerate design, and also to remain some flexibility on the design. Or and on the other side, if you want to design a compute platform for some the ground robots and very large scale robots. So in that case, the power consumption will not be the constraint. So we can use the GPU or the CPU to accelerate that. Yeah, so I think the takeaway here is it really depends on applications and the requirement. Is want to the high speed or the high accuracy. Yeah, so we will based on this metrics and requirement, so we can design our compute platform. Yeah, and I think my final goal of my PhD is to design a robotic SoC. So we want to integrate the different components, the CPU, GPU, and the this FPGA to build a robotic SoC to push forward this robotic computing.
Yeah, that's good. That makes sense.
Yeah, thank you.
All right, so then due to the time, I think we'll move on to the second presentation. Thank you. So by the way, VPN and the other judges, so the score sheet, right? So there will be 4 components. Maybe I'll announce this one more time. So there will be 4 components for all the students as well. So the first component, 30 marks for scientific novelty. The second component, a practical impact, also 30 marks. And then the third component, the presentation, 30 marks. And then eventually 10 marks, anything else you think is important. So this takes both the presentation and question answering into account. Yeah. All right, so I think we move on to the second speaker. Please go ahead and then share your screen.
Hi, am I audible and my screen is visible to everyone? Okay. Hi, this is Shal from ASU, and in this talk, I'll specifically present on the need and solutions for agile and explainable explorations for designing efficient AI accelerators. So with the rise in the embedded machine learning, domain-specific accelerators are increasingly deployed at the edge and IoT, and designing efficient accelerator appropriately is important for low price, smooth processing at the user end, like on our smartphones, and for energy consumption and sustainability perspective. So we need effective design space exploration or DSC techniques, and the DSC need to address several strict and often conflicting constraints and optimization objectives like latency, energy consumption, chip area, throughput, reliability, and price. So existing DSC techniques, they use black box optimizations, including evolutionary algorithms or AI approaches like Bayesian optimization and reinforcement learning. So these techniques, what happens is that they sample some configuration and then they observe the output and see what are the costs associated like latency. And then they try to acquire the candidates that can minimize the objective. But one key challenge is that they can know which trials reduce the objective, but they cannot reason about why. Like why the evaluated configurations cost higher, they cannot explain that, and how to address the underlying inefficiencies. So as a result, since we lack this explainability, they take excessive trials like many thousands of iterations or even days for a very vast search space like quadrillions of solutions in this deep learning accelerator design, and then still they could obtain solutions which are very far from the optimal. So our DSA framework here, it leverages the execution related characteristics from expert defined cost functions. And that is the key idea, that how we can enable explainability through bottleneck analysis, and we can achieve efficient and agile exploration. For example, let's say there are two factors involved, in this very mini example, which is showing actually exploring optimizing the latency for a ResNet layer. So there are two factors like compute time and memory access time. Now, if DSC could figure out that compute time is 4 times larger than communication time, then it could go ahead and increase number of computation units or number of accelerators by that much amount. Or if memory access time dominates or becomes the bottleneck, then it could apply some data reuse analysis and see can it increase the size of the shared memories. So with such reasoning, DSC can likely improve objective at every iteration, almost every iteration, and it can find outperforming designs in just fraction of the time. So, and in fact, we actually also provide and embed the bottleneck analysis to enable such exploration for deep learning acceleration domain. And you can see there is a reduction in latency at every attempt, and we can move from low cost region, high cost region to low cost region relatively fast and in a more systematic way. So application, I think another unique selling point here is that application can use multiple DNNs, our embedded and CPS applications, and then they can have multiple loop nests, and they significantly differ in execution characteristics. So actually we need to analyze the total execution cost. So if we just analyze single cost, it is not effective. So what our framework does is that it checks the bottlenecks for multiple workloads and their multiple functionality and aggregate them in meaningful way. And then we also provide the API and data structure through which our framework can be applied in any domain where designers can express such relationships and exploit the execution characteristics. And these are key results for edge AI acceleration. With bottleneck mitigation, it can achieve about 6 times low latency solution under constrained budgets, and compared to all ML-based and evolutionary constraint optimization algorithm. And it takes just minutes or 53 times less time, because it improves actually efficiency at every iteration by 30%. And then compared to off-the-shelf edge accelerator like HTPU or Iris, it improves area or energy efficiency by few fold or order of magnitude. And DSA is compiler aware. So there is a tightly coupled hardware software co-design, and solutions, hardware solutions that we explore are in tandem with mapping optimization. And finally, it can enable dynamic optimization opportunities needed by emerging use cases like runtime deployment or resource management on reconfigurable infrastructures for CPS. So I think that concludes my presentation, and thank you for kind attention. And I'm happy to take any questions or show demonstrations.
Very good, Sheldon. So questions from judges, please.
This is Vipin. So I have one question. If you go back to your previous slide, like you were showing results for different networks, right? Like I was kind of curious, like when I looked at this, why specifically, like, you know, the transformer network seems to be like, you know,
yes,
getting like specifically
yes,
like
yes. Thank you, excellent. So yeah, I think what happens is that there are often very similar layers like in transformers, or but I mean basically there are just encoder networks which are having very same size of the shapes of the tensors and same functionality. So actually mapping, so basically when we explore them, we need to just explore once. So there are very few unique layers as in. And then second reason is that the transformers involve matrix multiplication, which are 3-dimensional loops instead of 7-dimensional convolutions. So the search space for mapping optimization is also quite low when we do hardware software co-design. So these are, I think, two reasons, if I can elaborate well.
fair enough. Yeah, thank you.
All right, so let's move on to the third presentation, third student, Zhao Ying, please. So by the way, Yuan-Hao is supposed to chair this session, but he has another session to chair in Year's Week. So I'm taking his place. Yes, Zhao Ying, if you're ready, please.
Hey everyone, this is Zhao Yun from National University of Singapore. I'm advised by Tulika Mitchell. So I'm going to present one work from HPC 2022. It's called LISA, Graph Neural Network-based portable mapping on spatial accelerators. So now we can see a rapid increase of the accelerator. We have like a deep learning accelerator. It has an array of ALU and has a memory hierarchy for any deep learning, such like CNN, IM. And we also have a coarse-grained reconfigurable architecture, CGRA. It's for loops, similar to the deep learning accelerators. We have an array of PEs, and we have a on-chip data memory. And also we have like matrix multiplication accelerators. It's for special for matrix multiplication. So we can find that this accelerator share the common characteristics. It's like all of these accelerators have programmable processing elements. Deep learning accelerators have an array of ALU. CGRA has like a lot of PEs. It can execute any operation, and it can be programmable and flexible. And it has a network on chip to connect these ALUs or PEs to send the data through this computer unit. And it also has a scratch memory, that's an on-chip memory to store the data. So these accelerators have like a high performance, low power consumption for various kernels. Let's use the CGRA for a specific example. So let's say the CGRA has an array of PEs, and this PE can execute any operation, add, load, store. Let's say we have a kernel, it's a loop, and we can use the data flow graph to represent this loop. It has a load and to load, add, multiplication, and a store operation. Let's see how we can use this CGRA to execute this kernel. That means how to map this data flow graph onto the CGRA. First, we assign the node onto the PE, and we assign load, add, multiply, and store. Remember that each PE can execute any operation, so it's very flexible. And after we assign this operation, we use on-chip network to send data among PEs. That's called a root data dependency. And so it's a problem called mapping. We place this operation and the root data dependency. We can find it's the CGRA is very flexible, and we need to find an optimal mapping for this for any loop kernel. The problem is that we have various CGRA. This is so the 4x4 CGRA. We have like 2x2, 4x4, 8x8, 16x16 CGRA, and we have a different on-chip network. So let's say we can have a neighbor to neighbor, which means that we can send the data PE to its neighbor PEs. We have like a high cube architecture, which allows a single cycle multiple hops. That means it can visit like a very distant PE, and we have a different functionality, homogeneous and heterogeneous CGRA. So we can find that this CGRA actually is quite different. So however, when we wanted to map this DFG onto this spatial accelerator or CGRA, so we need to manually tune the mapper to adapt to the hardware characteristics. For example, like we have when we have a different CGRA size, we need to change the mapper and tune the mapper to find the best configuration, how to do it while utilize the resource. So, but we need to handcraft the mapper for each accelerator. But now, as I said, that we have so many accelerators, we can't tune the mapper for each accelerator manually. It's not good from time to market perspective. So we propose LISA, a learning-induced mapping for spatial accelerators. We propose to use the graph neural network to analyze data flow graph. That data flow graph actually, it's a data flow graph, but it's also a graph. So we propose to use graph neural network to analyze such graph. So we propose to use graph neural network to derive something called a label. It's designed by us, so it can represent the mapping impact of DFG structure. So then we design a label-aware mapper, so which connects the labels and the graph neural network to the mapping. So the label can exactly tell the mapper how to place nodes and route these nodes. So through the graph neural network, we can automatically tune the parameter for different accelerators. Let us use the example to show how GNN works. So GNN can collect the nodes and edge information and use aggregator to process information and update itself information and then propagate it. So let's say it's a graph, and each graph
One more minute, Joey. 1 more minute.
has some attributes, and we can like collect them and update them, and update the attributes, and so far we update once more and update again. So this is the whole framework of Lisa learning-induced mapping spatial accelerator. And let's focus on the performance. So in total, like we have 71 combinations of benchmarks, and the IOP can map 23, simulation can map 49, the Lisa can map 70 combinations, and the Lisa also achieved significant improvement on mapped DFGs. And also from compilation time, Lisa achieves like nearly 600 times and 17 times better than ILP and simultaneously. It's quite a standard algorithm. And actually this artifact is also available and won Distinguished Artifact Award. And we are applying this work into a black system autonomous driving platform. Okay, that's all. Thank you. I would like to take any question.
Right, thank you. So questions from judges, please.
Yeah, so just one question from me. Quick question. This work is is trying to use GNN as a methodology to do this mapping, right, from this software algorithm to the hardware, right? In this case, CGRA. I'm just wondering, in addition to your work, right, are there any other like state-of-the-art existing works that trying to do similar things, trying to map this DFG to a CGRA? Because from my perspective, I think there are many state-of-the-art works on this, which you might want to compare.
Yes, so we compared the two algorithm ILP and simultaneously, and it's quite like a popular algorithm used in the mapping. So we have like some other mapping algorithm didn't include here, but actually they are just for some special accelerator. They only optimize for their accelerator. They didn't adapt well for different accelerators. The IOP simultaneously are quite like a general algorithm. So we compare with IOP and the simultaneously. It's the two the most used algorithm. Did I answer your question?
Yeah. Okay. Yeah.
Okay. Thank you.
Okay, thank you, Xin. Thank you, Joy. All right, so we'll move on to the next speaker. Before that, just by the way, this is Wan Li. So I'm the Secretary Treasurer of ACM SIGBED. So I'm essentially representing SIGBED in this competition. And the champions in both categories will compete against representatives from other SIGs in the ACM finals. Right. So Lin, please share your screen if you're ready.
Okay, sure. Okay. Hello, everyone. I'm Lin Zhang from Syracuse University, and my advisor is Professor Fan-Xin Kong. And it's my honor to present our work, real-time attack recovery for cyber physical systems. And the cyber physical system integrates the cyber and physical components with sensors and actuators, which enable many new applications such as autonomous vehicle, delivery drones, smart grid, and you name it. And there are lots of sensors on the cyber physical system. For example, there are LiDAR, camera, radar, GPS on the autonomous vehicles. However, they are vulnerable to sensor attacks. And the attacker can manipulate the sensor measurement. And then the controller cannot get a proper state estimate. And the state estimate cannot reflect actual system state. So the controller will generate a control input sent to the actuator, and will drive the entire system deviate from the reference state and may reach the unsafe state, cause severe consequences like car accident and blackout. And the sensor attacks can be launched from the cyberspace and also the physical space. For example, the transduction attack is a very interesting attack, and it just manipulates the physical properties in the environment and can mess up the sensor readings. For example, the GPS spoofing attack can just like the autonomous vehicle can't get the actual location of the car and make the car drive out of the road. So it's very dangerous. And because all the cyber and physical components are intact, so the classical software security mechanism cannot detect or recover this type of attacks. So this just motivated many defense mechanisms such as attack prevention and detection, but attack response have been paid little attention. It's not consistent with its importance. For example, if there is a drone and if we didn't take any measurement after we detect an attack, it will hit the obstacle. So we need to extend the benefit of the attack detection and remove the negative impact caused by the sensor attack in real time to secure entire cyber physical systems. So our goal is to find a recovery control sequence that can steer our physical state back to the target site before a safe deadline, and even maintain in this site for a while after the attack detection, and also make sure our system state didn't reach the unsafe state in this entire process. So to tackle this problem, we just propose a new real-time recovery framework, and the attacker can arbitrarily manipulate the sensor measurement and then compromise state estimates. At first, there is no attack, so the system will run original controller, and the system state can follow the reference state. But at time t0, there is an attack, so the system state deviates from the target state. And then at time ta, we will detect state, and the entire system will switch from the normal mode to the recovery mode. And we use a state reconstructor to reconstruct state at tr, which is the initial state of the recovery. And also, we will use reachability analysis to compute a safe deadline, by which our system will not reach the unsafe site, and we should recover our system before that. Also, we will compute a maintainable time, and before that, we can maintain our system in our target site. After we get the initial state, the safe deadline, and the maintainable time, we can formulate the entire problem as an optimization problem. And by solving this problem, we can get a control sequence that can steer our system back to the target site and maintain in this site for a while. And next, let me introduce each component in detail. And the first one is our core components, is our recovery control calculator. We just formulate the entire problem as an optimization problem. And the objective is borrowed from the LQR method, including the penalty for the state and control input, which will make sure our entire recovery trajectory is very smooth. And we also consider the initial state and the target state. We want to let the system state back to our target site before the TD, and maintain in this site before TL. Also, we will make sure the system will remain safe during this recovery process. And so by solving this problem, we can get a recovery control sequence, and that can recover our system. And we also provide some theory and some formal proof in our paper. And the supporting components, such as the checkpointer, can record historic data. And based on this historic trustworthy data, we can just calculate our initial state of recovery at time TR using the reachability analysis. And after we get the initial state, we also want to calculate a safe deadline.
1 more minute, please. 1 more minute.
Yeah. By which we can just let our system to remain safe, and then we also want to calculate a maintainable time, and by which we can let our system to remain in this target site. And we evaluate our method on some numerical simulators, such as autonomous vehicle and delivery drones, something like that. And we can see our system can recover the system state back to the target site before the safe deadline. And we also evaluate our method in the high fidelity simulator, for example, at LGSVL. At first, the entire system can follow the line, and after attack, it will deviate the line. And also, we will recover the entire system back to the line. And we can also get a similar result from our robotic test bed. We can see our method can recover the robotic vehicles back to the line before a safe deadline and maintain in this line for a while. Okay, let's draw a conclusion. The most defense work are focused on the attack detection, and so and attack recovery work hasn't been paid much attention. So we just propose a new real-time sensor attack recovery work for cyber physical system. We formulate this problem as an optimization problem that can just get a control input, can drive our system state back to the target site before a safe deadline. And that is guaranteed by the formal modeling and methods. We also evaluate our method by some numerical simulators and high fidelity simulators, and also the robotic test bed. Thank you, everyone. Okay.
Okay, very good, Lee. Questions from judges, please.
Okay, this is Zhen from Wayne State University, and this is a very interesting project in real-time systems. So I have a very quick question, that is, can you intuitively explain how do you guarantee that the recovery can be performed or conducted in real time? Why it can be guaranteed? Thank you.
Okay, so real time means we want to just recover the entire system to our target site before safe deadline. And this is just formulated in our optimization problem. So we can get a control sequence, and that sequence can recover our system back to the target site before a safe deadline. And also another thing I think you also care about is the computational overhead. We just use some method like ADMM to accelerate the computational overhead, and we also consider the computational overhead in our formulation. We can see here. We just consider the computational overhead in our formulation. So we can accept some computational overhead, because our initial site of recovery is at time TR, not the time that the target is detected. So it allowed our use some time to compute the recovery control sequence. Yeah.
Yeah, thank you.
Thank you for your question.
Okay, thank you. Let's move on to the next speaker, Binit Ghosh, please.
I think you need to stop share so that I can share.
Yeah, Lin, yeah, please stop share.
Oh, I already stopped. Oh, sorry.
Okay, thank you. Hello, everyone. I'm Binit Ghosh, a PhD student from the University of North Carolina at Chapel Hill. My research focuses on designing and verification of autonomous systems. Today, I'm going to talk about an approach to design and verify autonomous system controllers under the presence of timing uncertainties. Imagine a scenario where a robot is trying to reach its destination, avoiding obstacles. The obstacles are given in purple and the destination is marked with a flag. The planned path of the robot to its destination is given in black. This we call the nominal trajectory. But the robot is running multiple jobs on its processor. It might be running jobs responsible for heat control or perception of the robot and several others, among which path follower is one. And this job is responsible for moving the robot along its planned trajectory. Since it's running multiple jobs together, it will not be able to schedule all the jobs at the same time, which results in deadline misses for some jobs. Now, what if the path follower misses its deadlines? If the path follower misses some deadlines, the resulting trajectory can deviate from the nominal trajectory, where the nominal trajectory is given in black. And the trajectory resulting from deadline misses is given in green, where we clearly see a deviation from the nominal trajectory. Now, what if the path follower misses more deadlines? Then the resulting trajectory can deviate more from the nominal trajectory and eventually become unsafe. Such a trajectory is shown in red. So in conclusion, we can say that not all patterns of deadline misses are safe. And the goal in this paper is to detect whether a given pattern of deadline misses is safe or not. To achieve that goal of whether or not given a pattern of deadline misses is safe, we compute the maximum possible deviation of the resulting trajectory from the nominal or the planned trajectory for the given pattern of deadline misses. If the maximum deviation is within a safe bound, then the behavior is safe. If not, it's unsafe. Given a pattern of deadline misses, we want to compute the maximum deviation up to a bounded time h. Consider a possible behavior given by this binary string of length h, where 0 represents a deadline miss and 1 represents a deadline hit. Therefore, a naive approach would require us to compute deviation of 2 power h many trajectories, which is clearly infeasible for practical values of h. Instead, what I propose to do in this paper is compute an over-approximation or an upper bound of the maximum deviation instead of the exact value. Existing benchmark approaches to compute the maximum deviation require computing reachable sets. The disadvantages of such techniques are the following. They are computationally expensive. Also, the computed upper bounds on the deviation are not tight. In comparison to other benchmark approaches, my contribution is as follows. I compute an upper bound of the maximum deviation for a given value for a given pattern of deadline misses. I propose a statistical approach to compute the deviation. Therefore, the guarantees are probabilistic in nature. Comparing my approach to other benchmark policies, I have the following advantages. This approach is faster than non-probabilistic approaches, and the deviation bounds computed by this approach is tighter. The overview of the proposed approach is as follows. The system model and the initial state is given as an input. Then we have three major components, the hypothesizer, the verifier, and the refiner. And finally, the computed upper bound on the deviation, which is represented by DUB, is returned. The hypothesizer module merely guesses a value of the maximum deviation. Note that it need not be correct. Then the initial guess is sent to the verifier module, which then verifies the guessed value of the deviation and this verifier is statistical. If the guess is found wrong, a counterexample, which is a trajectory that violates the guess deviation bound, is sent to the refiner. Then the refiner module refines the deviation using the counterexample and sends it back to the verifier for re-verification. And this process continues until a successful verification, at which the final upper bound on the deviation is returned. This approach can be further used to design schedulers. Recall, the robot was running multiple jobs together. As a result, some of the processes were missing its deadline, which resulted in safety violation. The goal here would be to schedule the jobs on a single processor such that none of the processes violate safety.
One more minute,
Now,
Vinny.
yes.
One more minute. Yeah.
Okay, yeah. Now that we have an approach to compute the safe behaviors for a controller, where a safe behavior means a pattern of deadline hits and misses, we can compute a safe behavior for all the processes using my proposed approach. And using these lists, we can compute an automaton that schedules all the processes such that none of the processes violate safety. In conclusion, in this paper, I propose a statistical approach to compute the maximum deviation under deadline misses. I observed in the experiments that we were able to compute tighter bounds with less computation time. Further, using my approach, we can construct schedules that do not violate safety. In future, I would like to consider more complicated patterns of deadline misses and more general schedules. The open source Python-based prototype tool is available through my public GitHub repository. Please feel free to check it out. Thank you. Any questions?
All right. Yeah, thank you for the presentation. Questions from judges, please. Do we have questions from judges?
I guess I'm this side. This is Vipin. I have one question.
Yes.
When you were mentioning about this parameter h, I was kind of curious. It looked like at the look back period, right? Like how far, like you get your
right. How far in time you would right.
Right.
How far in time?
So
yeah.
What factors like determine this h value, or like what goes into consideration when you?
So this is a user given parameter. So this is a user given parameter. So the user would want guarantee up to a certain time limit, and this time limit is represented by this h.
Okay, so it's like a QoS metric.
Right. Yeah. And for all the practical values of h, for instance, like 2000, brute force method would just fail.
All right, thank you. So we'll move on to the next speaker, Wen-Zhang, if you're ready, please.
Oh, okay. So, hello everyone. I am Wen-Zhang, a PhD student from Texas A&M University Corpus Christi. Today, I am very glad to present our research sustainable and intelligent IoT network. And I am advised by Dr. Chang. So as we know, with the development of artificial intelligence of everything, various embedded devices are deployed at each corner of our world. Those devices provide various observations of our life and on our Earth. However, because of powered by the batteries, those devices has a short lifetime. Energy harvesting devices that harvest energy from the ambient environment becomes a promising solution to realize the perpetual devices. Therefore, my research scenario, as this right picture indicated, a set of energy harvesting devices are specially distributed to collect data and then send the collected data to the edge server. So, our research aims to conduct the sensing strategy and the communication strategy for this mentioned system. So to reduce the energy cost and save more resource, we adopt the sparsity aware sensing instead of sense the full state data. That means we just only sense the sparse data when needed. The full state data will be reconstructed by the collected sparse data. However, even that the required amount of data is decreased dramatically by this sparsity aware sensing. Because of the intermittency of energy harvesting devices, the energy harvesting devices might miss the critical data sensing, especially when those devices are specially deployed and required to collect data at different time points. That means we need to simultaneously capture the spatial features and the temporal features. So to minimize the error between the reconstructed data and the real data, we have to answer two questions. The first one is what time the devices should sense while the energy harvesting device work intermittently. The second question is which sensor should be selected to sense. So our key idea includes two phases. In the first phase, we will have the historical data and then analyze those historical data to retrieve its aging modes. Through this aging modes, we can identify which time points and which locations are important for the reconstruction. Therefore, we can conduct a fixed sensing scheduling. After that, we will take this sensing scheduling as the suggestion, and then we will deploy the deep reinforcement learning agent to each device. That deep reinforcement learning agent will dynamically decide the sense at runtime. So the details as this procedure indicates. So after completing the sensing strategy, our second task is to build the communication strategy. So to reduce the energy cost on the long distance communication, we adopt the multi-hop communication. The transmitter, because of the intermittency of the energy harvesting devices, when the transmitter,
Please, one, yeah.
Just 1 minute left.
Yeah.
Okay, thanks a lot. So when the transmitter send data to the receiver might be sleeping. So we have to consider how much energy for sensing and how much energy for communication. Therefore, our strategy is upgrade the deep reinforcement learning agent developed at our first task, and to make it control our energy allocation and routing policy. But because of the diverse power traces for the energy harvesting device, like for each day, it has different power traces. It would lead to a complicated communication environment. Therefore, we would have a huge model size. At this time, the energy harvesting devices has a very constrained computing resource. Therefore, to simplify our model, we further propose the multi-modal framework. We will cluster the power traces into several sub-databases, and for each sub-database, we will train the corresponding model. Because each model only needs to deal with the similar case, therefore it would have a small size. So at our third task, we target on to complete the scenario that energy harvesting devices cannot reach out to the backbone of IoT. Therefore, we dispatch the UAV to assist the data collection. So at this phase, we will answer 3 questions. How many waypoints should the UAV visit with the limited duration? And the second question is, where should the UAV visit with the consideration of different capability of energy harvesting devices? Because of the different geolocation features, such as shadows, each energy harvesting device have the different power traces, which reflects the different capability on sensing and communication. So the final question we will answer is how to route those data into the UAV coverage. So I think this is our results. Anyway, our results shows like outperforms the baselines, but it would have a slightly higher overhead. So I think that's all for my work. And thanks for your listening. I'm happy to answer any questions. Thanks a lot.
Very good. Thank you for the presentation. So the questions from judges, please. Do we have questions from judges? All right. If not, then we will move on to the next speaker. So it's Nurani Soda. Please start if you're ready.
Hi, thank you, Wang Li. Can everyone hear me? All right. Hi, I am Nurani Sauda. I am a PhD candidate at the University of Virginia, and I am very excited to present my work today on Altair, an energy supervisor architecture for energy harvesting applications. We have seen over the past few years is that the potential of harvesting energy from environments is tremendous. This can literally take sensing anywhere from indoors to outdoors, but without the drawbacks of batteries. So batteries typically have a very short lifetime, which results in significant effort into maintenance. And when they run out, the tremendous amount of e-waste that is produced each year can be very harmful. So the question is that the energy harvesters, like the photovoltaic harvesters or a Peltier module, they were significantly different than battery power, than a battery. And usually during runtime, there is no guaranteed minimum supply of energy for the device. And with that, usually the amount of usable harvestable energy from environment is actually dependent on what source we harvest from and how the source changes throughout time and space. Which is why when we design energy harvesting devices, an application has to be fine-tuned into the expected energy conditions, which makes an application's logical flow very dependent on its energy states. Now, current existing energy harvesting designs fall short in several ways. First is that the existing power management hardware ICs, they have very limited functionalities. For example, they usually provide a few voltage rails that supply a regulated voltage and also a few trigger signals that the application can use to see if the energy storage connected with the device is sufficiently charged or whether it is overcharged or undercharged. But the device has no way to tell the power management IC that this is my minimum energy requirement and this is how the energy expense report of the device looks like. And the second challenge is that an application's logical executions becomes directly independent to its cautious energy states, meaning that the application has to keep checking what the current status of the energy storage is and determine whether to perform a specific task or not. And in this project, we argue that this fine-tuned coupling between the power supply and the application can restrict development in several ways. First is that now the application developer has to think about how to deal with energy uncertainty with an energy harvester and also fulfill the application level requirements. Second, with this intertwined implementation, you cannot really achieve independent power supply and application development. At the same time, fixed design or power management software can be very hard to translate to a new applications, which is why we argue that battery-less designs should find a balance between how much abstraction it should allow to the developers, at the same time optimizing for what control the application will have into the power supply hardware. With that, in Altair, we specifically implement energy management or optimization part separately from the application's code, with a clean interface between the application's requirement and the power supply interface. With this disentanglement, Altair introduces the concept of an energy supervisor that sits between an energy harvesting power supply hardware frontend and the main application that runs on the device. And the energy supervisor keeps monitoring the system energy and measures the system load power consumption and implements an online energy management algorithm to inform the application of its necessary parameters. So at runtime, the main application can use several APIs that the energy supervisor provides to ask for different energy related parameters. And the supervisor interacts with the low-level energy harvesting frontend, and it can be easily interchanged if now your harvesting modality changes. And the main application doesn't need to change anything if you switch to a different platform. Now with that,
Norani, one more minute, please. Yeah.
Yes, thank you, Wanli. Now at runtime, specifically, the main application can let the energy supervisor know about the acceptable duty cycles, the list of tasks that it is running, and if there is a list of required optimization algorithm. And the energy supervisor can let the main application know what the optimal duty cycle the device should be running in to achieve energy neutrality, which power mode it should run, and the underlying energy statistics on the storage capacitor. This is how we implemented Altair platform in a custom PCB and with a specific power supply interface that the application can use to integrate with the hardware platform. We integrated 6 different existing IoT devices and built 6 different applications. And these devices come from varying levels of different hardware and software flexibility. And we demonstrate that with different level of flexibility that these devices have, Altair can achieve a general reusable energy harvesting platform. And we also implement different energy optimization techniques showing that a power management software doesn't have to be specifically tied to a specific hardware platform, but it can be interchanged and modified. Now with that, I conclude this presentation by summarizing that Altair is a general purpose interface between an energy harvesting power supply and the running application. And it can enhance an energy harvesting power supply with the flexibility to retrofit existing applications by replacing batteries with energy harvesting functionality. Thank you so much. If you have any questions, I'm happy to answer.
Hi, this is a very interesting talk, and I have a simple question. So have you ever evaluated the additional energy consumption induced by the energy supervisor?
That is a very interesting question. So the energy supervisor does come with an energy overhead. So different implementation would result in a different energy cost. With the specific hardware that we designed, we did evaluate how much the additional energy cost of the supervisor itself would look like. But what I can remember, it was in the range of a few microwatts or so. But definitely it would depend on how much more power optimized the energy supervisor itself can be.
Yes, that's great. That can be ignored. Thank you.
Thank you so much. Thanks.
Wanli, I think you are muted.
Do you hear me?
Exactly. Yeah, it's muted. I didn't realize it. So yeah, thank you.
Okay.
Yeah, and questions and answers. So yeah, second, please, if you're ready.
Yeah, okay. So hello, everyone. My name is Sercan. I am from Istanbul Technical University and currently research scholar at the University of Louisiana at Lafayette. Today, I'm going to talk about stochastic computing. We have two major contributions on this. One is the agile stochastic computing simulation, and the other is the lightweight neural network design thanks to stochastic computing. Stochastic computing that dates back to 1960s is a re-emerging paradigm that uses the unconventional data representation, which means that we don't use base 2 representation of the data. So we don't have any bit significance for the bits, such as most and least significant bits. Instead, we represent data in the bit streams by assigning equal significance for each bit. Thereby, we are more robust to bit flips, soft errors. And we are using the cumulative counts of the ones to represent the probability value, thereby the stochasticity come from. The advantages of stochastic computing first is the fault robustness, and of course the low hardware cost, because we just use AND gate or XNOR gates for the multiplication. Thereby we have massive parallelism, scalability, and progressive precision. However, since we need to use long bit streams for high accurate results in arithmetics, we have the long latency. And we need to bit stream generators, thereby we have a cost for this. The results are approximate, and we have some energy issues, which is not in the scope of this work. Stochastic computing has multipliers as AND and XNOR gates based on the encoding sham. For example, here we have the positive only numbers, and we use the AND gate for multiplication. We represent scalars in the bit streams. So the 4 and 6 is the exact amounts of the ones throughout the bit stream. Here is the bit stream size is n. When we end these bit streams, the output bit stream is actually the multiplication of the probability values under the assumption if we have the uncorrelated bit streams. For the negative numbers, if we have also negative numbers, we need to use the bipolar encoding. So again, we need to use the uncorrelated bit streams to have the multiplication at the output as the multiplication of probability values. For bipolar encoding, I need to underscore an important point. It doesn't have any sign bit, which is a very advantageous, because it's again robust to bit flips. It instead just use the majority or minority of the ones for this sign information, which means that if we have ones in the majority, we have the positive number. If we have ones in the minority, we have a negative number. We are solving two problems in this work. One is the long length bit stream simulation, which causes the runtime and memory problems, thanks to contingency tables that we propose. And the second problem is based on the binarized neural networks, because binarized neural networks has single bits, which are fragile in emerging platforms such as ReRAM technologies in memory computing. This is the reason why we propose to use bitstream processing. The first contribution is based on the contingency table. We, instead of generating and processing the bit streams, we just use the scalar values from the inputs itself and the correlation information. And we have a table which holds A, B, C, D values, that these are representing the 1, 1, 0, 1, 0, 0, 1, and 0, 0 overlappings on the bit streams, which are not produced and processed. By using only the scalar values, even though we don't process the bit streams, thanks to the CT construction, we have the logic output at the end of any gate. So we have the CT logic. We first construct the A value on the contingency table construct based on the minimum, maximum, or zero correlation, thanks to stochastic cross correlation metric. And then we find B, C, and D values. Thereby we have all these 4 CT construct elements, and we have the CT logic. Here we have an example as a result. In a convolutional neural network for the classifier part multiplications, we have XNOR gates because we need negative numbers. We compare the bit stream processing, actual bit streams, and the CT-based multipliers. So we have the speed up to 78 times when we have the 1024 bit stream size in a stochastic bit stream based neural network for the training. So overall, we have just a linear time for for the bit stream size, increasing bit stream size. However, for the actual bit streams, we are exponentially depending on the bit stream size. The other contribution is based on the binarized neural networks. Different from the prior art, thanks to bipolar encoding, we don't use the threshold and the subtractor module in the hardware design. Instead, again, we use the population count for the bit streams, but we just add a masking logic to decide whether the majority or the minority of ones present in a bit stream. So here is an example. X and Y is the input and the weights of a neural network. So after we make the multiplication by XNOR gates, we just concatenate the incoming bit streams. And by using a population count, we just count the logic ones. And at each count operation, we control whether we are bigger or less than the half size of the bit stream, which means that +1 or -1. So instead of using a subtractor, we just concurrently control the population count and then decide the neuron activation for binarized neural networks. There are two advantages when we use this structure. The first is the hardware efficiency, because we don't use the subtractor. Up to 30%, we have hardware resource utilization, better resource utilization in terms of lookup tables and registers. Plus, we are more robust to soft errors. For example, when we inject bit flips to the images that we process, by using just a 16-bit bit stream processing binarized neural networks, we are just 2% less than the conventional reference accuracy value. So we even can further increase the bit flips, not only for image, but also the weight bit flips. Still, BSPNN 16 is more robust to errors. And we also propose with error training in the paper that I show here. These are my selected works based on this topic. And thank you very much for your listening.
Thank you. So questions from the judge panel, please.
Yeah, quick question. So we know there are already like many works on using stochastic computing for neural networks. So what is the uniqueness about your work, using stochastic for computing for neural networks here? And how do you compare your work to the other existing stochastic computing based neural networks?
Yeah. Stochastic computing works generally using the kind of full precision or quantized neural networks, but there are also some prior works on the bit stream processing, but they never use the bit stream processing throughout all layers. They just use the data in stochasticity, but we just use these 8-bit, 16-bit representation throughout the network. Thereby, we don't use the subtractor value. All binarized neural networks, not only for stochastic, but also the conventional networks, always trying to use the comparing with the threshold value, but we never do it. So the most important part in terms of the neural networks is we don't use extra activation module for this decision. We concurrently do it during the accumulation.
So you're saying all the existing works, they use activation, but here you don't need activation.
Yeah, exactly. As far as to the best of my knowledge, there is no work that's proposing something like this. So we don't use any activation module. We have just a masking logic in the accumulator. So we are just using the less hardware cost thanks to this approach. Of course, we also have some soft error robustness to bit flips.
Okay.
Okay, very good. Thank you.
Thank you very much.
Yeah, so let's move on to the last speaker of session 1. No, okay, so this is already the last speaker of session 1. So I think we have successfully completed session 1, which is an online session.
I'm sorry.
Yeah, Yujie, I think you'll be session 2. You'll join session 2, but you can join from online. That's no problem.
Okay. Yeah.
Okay. Yeah, because you can't make Shanghai. That's fine. So let me conclude this session. Thank you very much, all the students and especially the judges. So we'll wrap up this session, and then session 2 will be on site in Shanghai, and then in the afternoon there will be the third session, which is meant for European participants. So the judges, please, after this session, send your score sheet to me, and then the results will be announced in the award ceremony of ES Week, 11 p.m. Today, Shanghai time. Yeah. Okay, so then this will be the end of this session. Thank you once again for joining, for all the excellent presentations, questions, and answers. Thank you. Hello. Right. Okay, I think we can start session 2. This is an on-site session in Shanghai. So we already have the first speaker on the stage. So please start if you're ready. I'll share the screen.
Okay, so hello everyone. My name is Yuan-Hao, undergraduate student from Michigan and the Shanghai University Joint Institute. My topic is real-time scheduling of fixed priority tasks on heterogeneous architectures. Okay, thank you. Yeah. So autonomous driving, robotics, and many other artificial intelligence tasks has been quite popular these days. Among those tasks, the serial computation segments are usually allocated to CPU cores, while data parallel. Okay. While data parallel segments will be uploaded to the processing elements. This interleaved execution pattern aggregates the dependency and computation between the parallel tasks. Okay, so first thing is the time dependency. That is, we need to finish the first segment before we move on to the next part. Here we use a CPU-GPU system as an example because it's the most widely used heterogeneous system or cyber-physical system. Another point is resource computation. In CPU-GPU system, when one task visits GPU or memory, it might occupy all the resource and block other tasks from visiting it. It will therefore lead to a very low utilization rate, and it will be nightmare for multiple task co-execution. Such complicated task execution pattern makes it difficult to achieve both timing constraints and a high resource utilization rate simultaneously. Therefore, we propose a scheduling strategy integrating the temporal access to CPU cores and the spatial partitioning for processing elements. For CPU part, we consider all CPU resource as a pool. Each task will occupy part of the resource, and a higher priority task would suspend the lower ones. And resource partitioning is conducted on GPU part. That is, all the tasks share the GPU resource. After resource partitioning, those tasks can run parallelly on the GPU system. At the same time, I've done some work on energy side. The overall strategy is to dynamically adjust the GPU frequency and the voltage according to the difference between the expected and the actual resource time. Thank you. So the main idea of our work is to calculate the workload of higher priority tasks with a given time interval, and we compare that to the total computing resource to check whether there is spare computing resource left for the current task. And in this way, we can find out what time the current task will finish another 1 unit of execution. The proposed scheduling is evaluated on a real computing platform. First, for the uniform task set, the parameter is shown here. The black curve at the very right is the performance of real system, and the second red curve is our algorithm. The dashed area here shows the improvement compared with the existing approaches. And our work behaves well as the segment number increases. For versatile parallel task, our work still we generate the task based on a classic convolutional neural network topology, and our work still works well in this case. And on energy side, the experiment is conducted on NVIDIA Jetson GX2 board. As can be seen from the figure, there's a significant downregulation of GPU frequency. And the overall energy saving is around about 20% to 40%. So the main contribution of our work is that first, we proposed a scheduling strategy with federated and fixed priority scheduling, and also energy efficient energy scheduling strategy, which significantly reduced the power and energy consumption of the heterogeneous platform. Sorry. Second, an end-to-end response time analysis is performed, leveraging the workload function in self-sufficient models. And third is that extensive numerical and real CPU GPU experiments are conducted to demonstrate that the proposed approach can improve schedulability on both unified and versatile parallel tasks, and effectively reduce the pessimism. And the energy side work can reduce the energy consumption while guaranteeing the schedulability. Thank you, and I'm happy to take any questions.
Very good. Thank you. Questions from the judges? Okay, thank you for your excellent presentation. Thank you. And my question is that you have done good work to considering the resource computation in the multi-core task scheduling, right?
Yeah.
And you consider the saving energy and enabling the scalability, right?
Yes.
And my question is that have you considered the energy saving in the scalability process, the scalability analysis, or you consider the saving energy and scalability analysis as two separate issues? Which one is right?
Thank you for your question. So first, I will explain it in this way. So the first part of our work is like we do for the parallel task, we do simulations based on our scheduling strategy, so that this kind of scheduling strategy is more on simulation part. And I think this can be further introduced to the real system on the real system on the CPU GPU system. And in this way, we can, based on the simulation results, it can help us reduce the energy consumption, and while guaranteeing the scalability. And the scalability part is not demonstrated in this PowerPoint, but we've done experiments on both sides, on both with and without GPU frequency adjustment. And the outcoming curve is quite like this. The outcoming figure is basically the same under different parameter settings, like different segment numbers or different task sets. And in this way, I think we can achieve the energy consumption saving, as well as the scalability. So yeah.
Okay, thank you for your answers. Okay, got it. Okay, thank you for questions and presentation. So we have actually a mixture of undergraduates and graduates in this competition, and this student is under the undergraduate category. Yeah, thank you. So we'll move on to the second speaker, please.
Thank you very much.
start if you're ready.
Wait, okay. Hello everyone, good morning. Today's my topic is an advanced driver assistance based on Contingency gateway. My presentation includes 3 aspects. First off, introduction. With the intelligent development of vehicle, various sensors are introduced into vehicle electronic systems, such as ADAS. The ADAS sensors include camera and radar. The higher requirement for the vehicle network are the higher bandwidth, real-time, and the reliability and security. The motivation and the contribution of our work are below. The ADAS with centralized domain controllers is single function and is difficult to communication with other domains. The ADAS is based on infinite transmission, so it has unsecond delay and without time synchronization mechanism. In our work, we will shift a cross-domain multi-sensor fusion and use a time-sensitive network to ensure real-time communication. Our systems divide into ADAS, vehicle control system, and central gateway. The camera is used for traffic information detection and the driver behind the detection. The radar is used for the object detection. The TSM protocol we use include AS and QBV. Before the multi-sensor fusion, we should assume CAN-TSM protocol conversion at first. The CAN-TSM is used to multi-sensor fusion. The TSM to CAN is used for the transmission control the flow. Next one is the multi-sensor. Next one is the multi-sensor fusion. In our system, the radar transmits point cloud data and the output include the location and the speed. The camera transmission image data and output include the location and the category. We use the coordinate transformation for the location data fusion. As for the time synchronization, we use the Linux PTP synchronization software such as PTP4L and the PHC26. We use PHC to get the timestamp from media access control layer, add the timestamp to message, and use the socket to transmit the message. We use the time-aware shape to ensure real-time communication. Our system identifies the TSM thread through the VLAN tag and put the thread into different output queue. Schedule the thread output according to the current gate state. We record a demo video. Let's take a look.
Our system include advanced driver assistance system, vehicle control system, and central gateway. We use PTP to achieve time synchronization. At first, it was not adjusted, and then it reached a stable state. After several adjustments, through clustering algorithm, we obtained the obstacle information from the original data of millimeter wave radar. We put the camera and the millimeter wave radar together and use the sensor fusion algorithm to obtain the category distance and speed of obstacles for decision making.
That's all. Thanks for listening.
All right, thank you. Questions? Okay. Thank you for good work, and you have done very attractive demo, right? And my question is that also the TSN network has been proposed for decades, you know, and but how to implement it in a real world vehicle? Maybe this is a very difficult problem to answer, and you can try your best. Okay.
Yes, and we use the time-sensitive networks to ensure real-time communication by the time-aware shape and time synchronization and the time-aware shape. That's all.
Thank you.
Thank you.
All right, so then let's move on to the third presentation. Yeah, start when you are ready.
Hello everyone, I'm very glad to attend the SRC. I'm Xiong Chenai from Hunan University. My topic is ZVM, the Zephyr-based virtual machine manager. My presentation is divided into 3 parts, and first we introduce the background, and with the embedded process provide powerful computing abilities, and it makes the embedded system more complexity, like the intelligent factory and the intelligent vehicle. And this complexity makes some real-time security issues, and the hardware is an effective method to address this issue. And existing hardware like KVM and the current hypervisor has some advantages and some disadvantages as below. And we developed the CVM to integrate the advantage of the 2 typical hypervisors for the below features, like long overhead, high real-time, high security, and good adaptability. And our contribution is below. First, even in the type 2 hypervisors based on the widely used open source RTOS, and developed is easy to access it. And second, the lightweight design for the hypervisors make the hypervisor suitable for embedded systems. And for the body part, and that is my systems, our systems architectures. There are 4 layers, and the most important layer is the ZVM mode, include the virtual CPU, memory, and interrupt, and the I/O through mode. And the ZVM has the below features like isolation, real time, and lightweight, and customizable. And then we will introduce the main work that the sub-mode designed for the CPU mode. And we designed the CPU bound to a host thread and scheduled by host, and use VHE support to reduce the context switch. And for memory mode, we use 2-stage translation for GV to the HPA for the VM, and use several structures to design to record the HPA and the HPA in the VM. And for the VRQ mode, we designed that all interrupt are routed to the hybrids, and the hybrids judge the injection of the VRQ to the VM. And for the VIO mode, we designed 2 types of devices. One is the fully virtual device, and the second is the device pass-through to reduce the latency. And that is the main work of then we will introduce the demonstration. There is a supported platform that we support for list on the right, the RFP equipment and the rock chip SoC, and the left is the use case for build the event on Linux. And we will show the detail on the below video. And let's take a look at the video. This we can see that in the terminal 0 is the VM host, and the terminal 1 is the terminal 1, 2 is the VM, and we use the VM command to control the virtual machine. And just like VM info and VM new and VM run. And you can see that we put the VM. Let's show the first command, and we put a Linux VM. Now this is to show the Linux command. And that's all. Thanks.
Yep. Thank you. Questions? Okay, you have done a very important work, right? And you know that the basic software in the intelligent vehicle is heavily supported by our government, right? My question is that the hypervisor are formally used for the cloud, right? For the cloud computing, and I know it is very difficult to adapt it to support the embedded systems. And the most important thing to support embedded system is to consider the limited resources, right? For example, the memory and the communication resource, and how to deal with this.
Oh, yeah, that's a good question. That we can see in the slide that just like the slide showed, we consider the light value mainly in two parts. One is the small code and the image size of the level OS, and we our works code size is small too, and the context switch that we consider in this system, and is using the ARM bar hardware visualization support that make it easy to reduce the resource consumption. That's all.
Okay, thank you.
Thanks.
All right, thank you. So the fourth speaker is from online. Yeah, you can start if it's possible.
Yeah, okay.
Right, so this is another undergraduate student, right? Yeah, please.
Okay, thank you. Ladies and gentlemen, I'm Chang Yujie from Nanchang University. So my topic today is the energy efficient and fair version control for distributed UAVs. So let me start with the research background. First, AI is developing rapidly and are widely used in the field of UAV cluster. And second, the computational demands are rising and system management is becoming more complex. Third, when facing these challenges like the optimization of energy consumption or scheduling in multitask collaboration, we may have these questions to be dealt with. So in our preparatory work, we find that the motor and the onboard computer are the main sources of the working power of the whole UAV system. So if we want to control the UAV by adjusting the throttle point, and the power will be changed a lot in a few seconds. So we think that it's difficult to optimize the energy consumption from the hardware level. And so we want to optimize it from the software level, especially based on multitask updates that aims to provide a new idea for the management of the computing system of the UAV cluster. So here comes to the problem definition. How can the system achieve dynamic adjustment of the update policy and so as to minimize the energy consumption while ensuring the fairness? So we have many challenges to ensure fairness, to balance between the opportunities and the energy consumption, and to handle the impact of the execution possibility of a task on its update value. So we have the system design. The first is task classification. We divided these tasks into two categories. One is the local task, which corresponds mainly to the basic functions like formation change, and the other is the external task, which mainly corresponds to the additional functions. Attention, so each external task only corresponds to only one additional functions. And we applied reinforcement learning in our system, and we just divided the framework into two layers. The one is the global layer. When the external task come into the global layer, it will assign multiple external tasks into individual nodes. First is broadcast these updates, and according to the current state, to calculate the value to adjust the update policy. And the local layer will arrange the order between these tasks and just execute them. And after that, the UAV cluster will feed the state back, including the software version and the energy consumption. So this become a new state, and this made it a circle. So that's how our framework works. So we redesigned the reward function, and a lot of variables just place different important roles in the function. And that means different tasks in different times of different software version, we have different update value. So we want to adjust the relationship between the positive value of the update and the negative value of the energy consumption. And we have some experiments, simulations. The first is the settings. We compare with the random selection, reinforcement learning, and static selection group. The static selection means that in different times, the system will choose their update policy in a static way, just have the stable choice. And and each iteration we have 15 broadcasting. And attention, we noticed that these 3 broadcastings are invalid because we want to simulate that if the system cannot work properly, how can our method provide better results than other group? So here's come to the results. The first 2 pictures shows that our method can save a lot of energy. That means this is energy efficient. And second, is about the fair. From this picture, we can see that the energy saving does not come at the expense of a large number of decrease in the update chunks of each task. And from the CV, they all below 8. And we can say that different tasks can have fair update chances. So we think our method is fair. And the last is the dynamic. When the system occur abnormal circumstances like that, we can see that from the result, our method can provide different tasks a fair chance for update. So this is our work's characteristics. So here is our team, and that's all for my sharing. Thank you for listening.
Here you show the power consumptions of the motor and the processor. Can you come to slide 2? I remember that you note that the motor takes about over 100 watt power, but the processor takes about 5 to here. So processor takes about 5 to 60 watt, right? So can you explain when the processor can reach about 60 watt? I think that will be a very large value for the embedded system.
Yeah, because in many circumstances that the computational demands is rising in this like UAV cluster, and when we want to we can imagine that a scenery when some place the earthquake happens in some place, and our UAV cluster can provide communication service for the people here. So in that circumstance, the onboard computer will consume a lot. That is also a tendency for the UAV cluster. The working power will be rising, and in a few years, I think so. We consider from this part.
Okay. Okay. Thank you. I have another question is for your experiment. So, may I ask, did you perform the experiment on maybe some simulation tool or on a real system?
Yeah, you mean the experience result?
Yes.
Yeah, actually, we do a lot of simulations through Python or MATLAB, and because we think that the cost of the UAV cluster is relatively high, so actually we do not purchase a large number of UAV. And one of the research of one of the research direction of our library is distributed systems. So we hope to start from the direction of the system design and provide a new idea. This means that we are not concerned with the execution of the tasks, but rather than the allocation of the tasks. So in practice, the software version and energy consumption I have mentioned before can be directly obtained by the system in real.
Oh, okay. Thank you. That makes sense. Okay. Thank you.
Yes. Thank you.
All right, thank you for the presentation and questions. So now we have the last speaker of session 2. Right, so start if you're ready.
Hello everyone, I'm Fang Yin. I come from the Hunan University. It's a great honor to introduce our work to every expert and professor. Yeah, problem on scheduling a parameter program. A parallel program represented by weighted directed cycle graph onto a set of processor to minimize the completion time of a program has been extension scheduling. The exciting result widely used in aerospace, wireless communication, and universal computing field. Well, most existing scaling algorithms often use the data generated by different data generation methods. This math could not cover data with all possible internal structure, make performance incomparable. Therefore, that generator is required to achieve unified comparison of different scaling algorithm. The generator needs to satisfy the following conditions. First, that generator needs to cover all that task model internal structure, and then that generator needed to generate actually constrain the characteristic of the type. And the last, that generator need to have a high work efficiency. Now I will introduce the exciting research, some exciting researchers. As illustrated in table, we can see the parameters such as the number of nodes, the number of the edges, and the length of the dial, which is the number of the nodes in the critical path of the dial, and the characteristic about the space and the degree, which has received extensive attention from the researchers. But the existing data generator there has the following problems. First, they have less controllable parameters, such as this generator all cannot constrain the width, which is a significant characteristic of the dial. And then the generated data is hard to cover all possible data that's internal structures. And the last, the generated result may be outside the scope of the data, such as they can generate unconnected graph. I introduce we work named the versatile random data generator. To address the problem with the exciting data generators, we propose a data generator named the versatile random data generator. First, in this work, the data generator we propose has more controllable parameter as shown in the table 2. For example, the number of the data nodes, the length of the data, which is the number of the nodes in the critical path, and the node we control the width of the data. Versatile random data generator can obtain all feasible solutions which satisfy the constraints and completely cover all possible data structure. And last, the data generated by versatile data generator strictly by the given constraint. There are no results within unconnected graph. So the versatile data generator we proposed through the adjustment matrix of data based on the satisfiability module threads the structure about the adjacent matrix as shown in figure 1. We take some constraint of the adjacent matrix. The basic constraint, constraint is the lower triangle matrix must be 0, and the element in the diagram of the adjacent matrix must be 0. And we control the width of the diagram. We control the width of the diagram and the connected radius and shape and degree, out degree and in degree and jumper level and so on. So we take some example. We take the node num. The node number of the nodes of that is 9, and the critical path node is 5, and another parameter and so on. We can say the data distribution of the number of the edge is shown in the following figures. Thank you.
All right, very good. Thank you for the presentation. So questions from the judge panel? Okay, very interesting work. And we all know that the DAG model is very practical in the real world, right? And from my side, what I concerned is that how to motivate from the real world is more important. And my question is how to map the real world applications to your formal model.
Thank you.
Yeah, I know well about your life, and you do very solid work in your life. Okay.
Yeah. Thank you. In the real world, our work will take in the some simulation and take some list scaling algorithm to use that task model.
Right, and you know that the real world applications can be formulated as the DAG and can be generated by the existing method well. And what features cannot be captured by the already known method, and what the new feature can be captured by your model?
In future, our model will take some code example, and we will abstract the code, the real world code, and to that model, and use that model to test the scaling algorithm performance. And so.
Okay, thank you. All right, thank you very much. So we are close to the end of this session. So it's almost 12, exactly 12 actually, exactly as planned. So I would like to thank all the speakers of session 2 again, and especially our judge panel. Then we will wrap up the sessions, the 2 sessions in the morning, and then we'll see you at 2 p.m. There will be the last session meant for European participants. Right, thank you.